Our next talk is from Junseok Kim, who will be talking about non-relatively hyperbolic hyperbolicity of automorphism of automorphism groups. So go ahead.
Okay. Thanks for the invitation, and I'm really glad to be here. So the title of this talk is Non-Relative Hyperbolicity of Automorphism and Outer Automorphism Groups of Right-Angle Artin Groups. Our main goal is that we'll see how to figure out the non-relative hyperbolicity of those groups, and because we don't have enough time, we'll do some easy examples to verify that property. This is joint work with Sangrok and Philippe Tranchida. The content is based on the paper uploaded on arXiv, and I will write the link in the chat window. Wait a second, please. Okay, let's start. First, let me check some basic notions. Here f sub n is Rankin-free group, and g to the n is the Rankin-free abelian group. Also, out fn, and J and G are automorphism and outer automorphisms of automorphism groups of them. And next, to define a right-angle Artin group, or simply reg, we denote that the capital gamma is a finite simplicial graph, and V is a vertex set of F, and E is a S set of gamma. Here's the definition of right-angle Artin groups. A sub gamma is a group generated by the vertex at V, and the relation is given by the edge connections in the graph. The group made by this way is called the right-angle Artin group associated with gamma. If the associated graph is discrete, like this, with 5 vertices, then we obtain the free group with length 5. And if the graph is complete, then we get a free abelian group, and F2 cross F2 is also the right-angle Artin group associated with the graph given like this. These are some easy examples of right-angle Artin groups. So here's the motivation of this research. As the free group, Fn, and free abelian group, Cn, are really basic objects in group theory, so it's really important to understand them. Of course, one way to understand them is studying their automorphism and outer automorphism groups. However, even though they look different, their outer automorphism groups share many common properties. For example, virtual torsion freeness, residual finiteness, and finite virtual cohomological dimension. Instead of understanding the meaning of these properties, we focus on the other natural question that, do these groups share any other property? Interestingly, we found a theorem saying that if the rank is not small, then these groups are not relatively hyperbolic. And before, we saw that the free group and the free abelian group are examples of right-angle Artin groups. So understanding their automorphism group and outer automorphism groups may help to understand out Fn or out Fn or GL and G more generally. And this viewpoint gives another natural question then. Which property holds for out A gamma or out A gamma? Surprisingly, the properties which I mentioned in the previous slide hold for any out A gamma. As out Fn and out Fn and GL and G are not relatively hyperbolic, we can ask whether odd A gamma or out A gamma are relatively hyperbolic or not. These are the general motivation of our research. Is there any questions so far? Okay, then let's continue. Before the answer, let me define the relative hyperbolicity of a group. There are many definitions of relative hyperbolicity, but we only refer to the definition made by Vertices. Assume that G is finitely generated group and H is a finite collection of finitely generated proper subgroups of G. Denote capital lambda is the calligraph of G with respect to S. So now let's define the conduct calligraph first. Actually, this is not a simplicial graph, but it's just a metric space. Okay, so starting with lambda, starting with the calligraph lambda, and we add each coset as a vertex in the new space. And you make an edge between the coset and an element contained in this coset. And the edge obtained by this way is has length 1/2. This space is called the conduct calligraph. That's the definition of the conduct calligraph. And here's an example. Let's first consider Z square with the standard generating set 1, 0 and 0, 1. And H is the diagonal subgroup of Z square. Here the black lines represent the calligraph of Z square, and the red line represents the diagonal subgroup H, and the blue line represents the coset 0, 1 H because it contains a 0, 1. Because the vertices on the red line are contained in H, we connect them by edges with length 1/2. Similarly, we connect them by edges of length 1/2. This picture is the conduct calligraph of Z square. And note that if we consider the edge connecting 0, 0 and 0, 1, and then for any non-zero integer n, we can make a corresponding cycle with total length 4. This kind of cycle is appeared in the definition of the relative hyperbolicity. That's why I mentioned it. And here's the definition of relative hyperbolic groups. If we satisfy these two conditions, then we say that G is strongly relatively hyperbolic with respect to H. At first, we need delta hyperbolicity of the conduct calligraph for some. Delta. And secondly, the conduct calligraph must be fine. It means that for any positive integer k, and all edges of conduct calligraph are contained in finitely many simple cycles of length k. And if the group G satisfies only the first condition, we say that G is weakly relatively hyperbolic with respect to H. In this talk, we only consider strong sense, and it seems a bit complicated, so let's refer to the previous example. The edge here, joining 0, 0 and 0, 1 are contained in infinitely many simple cycles of length 4 because we assume that n was arbitrary. So the second condition does not hold, and so thus the z square is not relatively strongly relatively hyperbolic with respect to the diagonal subgroup H. In fact, z square is weakly relatively hyperbolic with respect to z H. But let me skip the details. In general, if the group G is not relatively hyperbolic with respect to any choice of H, then we say that G is not relatively hyperbolic. Moreover, notice that any hyperbolic group is relatively hyperbolic with respect to the trivial subgroup, because the trivial subgroup doesn't play any role in the conduct calligraph. However, using the conduct, a hyperbolic group is impossible to be not relatively hyperbolic. However, using the conduct calligraph, it's really hard to see directly whether the group is relatively hyperbolic or not. So we'll use some criterion to verify that kind of problem. G is finitely generated group again, and the generating set S must have only infinite order element. That's a setting, and the definition of the commutative graph K is that the vertex set of K is just a generating set S, and we make an edge joining small s and small s prime if they're integer exponents of them, such that they generate the abelian subgroup of G. That's the definition of the commutativity graph. Note that if S and S prime commute, then because n sub S and n sub S prime is just 1, they can be joined by an edge directly. So, and I will use this idea in the proof. Next, and with the same setting here, here is the criterion made for non-relative hyperbolicity proved by Anderson, Aramayona, and Shackleton. Suppose that the commutative graph is connected, and for some generator sets and S prime, if we take some powers of them, then it generates a rank 2 free abelian subgroup of G. Then the theorem says that under these conditions, we get non-relative hyperbolicity of G. That's our main tool for verifying the non-relative hyperbolicity of a finitely generated group. Okay. Any questions? Okay, then let me continue. Using these tools, we want to see whether out A gamma or out A gamma is not relatively hyperbolic or relatively hyperbolic with respect to something. In order to use this criterion, we should check these groups are finitely generated or not first. Fortunately, for any graph gamma, out A gamma is finitely generated. Of course, out A gamma is also finitely generated. In fact, there are 4 classes of automorphic generators. In fact, there are automorphisms of right-angle Artin groups called graph automorphism, inversion, transvection, and partial conjugation. Instead of defining them now, let me give some brief explanation of them. Here's a simple example. If the graph is given like this, I wrote 2 automorphisms here. The first one the first one solves B and C, and this is an example of graph automorphisms. Graph automorphism. And the second one sends A to A inverse, and it fixes other generators. This automorphism is an example of inversion. Actually, transvection and partial conjugations have infinite order, but as you can see here, the graph automorphisms and inversions have finite order. So we have to remove them as generators of the group to use the criterion. But we can use this idea because of the following theorem and lemma. As being not relatively hyperbolic is a quasi-isometry invariant, it is enough to find the finite index subgroup which satisfies the assumptions of the criterion. Here's such a group, A star, out A star, out star A gamma. Actually, this group has generators, just transactions and partial conjugations. Since these groups, out A gamma and out star A gamma are quasi-isometric, so we can deduce that out A gamma is not relatively hyperbolic if and only if out star A gamma is not relatively hyperbolic. If a star has the connected commutative graph, and if it satisfies the rank to prevalent group condition, then we can deduce that out A gamma is not relatively hyperbolic. And that's our main strategy. So let's see. And it turns out that if the associated graph has at least 3 vertices, then out A gamma is not relatively hyperbolic in general. It's hard to give the whole proof in this talk, so instead of it, let me give a simple example. Gamma is given like this, and one of the generators called transvection is denoted by T sub AB, and it sends A to AB, and it fixes other generators of gamma. Actually, in this case, there are only 4 transvections: T sub AB, T sub BA, T sub CD, and T sub CD. There are only 4 transvections in out star. Moreover, by some reason, partial conjugations denoted by P sub some vertex, it is the same as inner automorphisms, and these P sub A, P sub B, P sub C, and P sub D are only partial conjugations appeared in out star A gamma. Note that T sub AB and T sub BA, as you can see here, they fix C and D, and vice versa, T sub AB and T sub CD commute. So here's a vertices of commutative graph, and so we get edge like this, right? And because A and B commutes in the right-hand Artin group, so PA and PB also commute. By the same reason, P sub C and P sub D also commute, and by some calculation, you can check that T sub BA and P sub A commute, and T sub DC and P sub C commute. Maybe there are more edges in the commutative graph like this, but it's already enough to see that the graph is already connected. So, and in addition, you can easily see that T sub AB and T sub CD generates the group generated by T sub AB and T sub CD generates rank 2 free abelian subgroup. Therefore, by the criterion for this graph, we deduce that odd A sub gamma is not relatively hyperbolic. Okay, and that's the whole picture, little whole picture of odd A gamma. And but for out A gamma, some out A gamma can be relatively hyperbolic. Indeed, if the graph is a cycle, like this, with length more than 4, then out A gamma can be a finite group. Or there are some cases that out star, which is the quotient image of a star, is just Z in this case, and in this case, out star is isomorphic to GL to Z. Actually, since finite groups and Z and GL to Z are hyperbolic, there's some kind of exceptional cases. But it's really lucky that these are only exceptional cases. Here's the theorem related to that. If the graph has more than at least 2 vertices, and except for some cases that I mentioned above here, then out A gamma is not relatively hyperbolic. Let's see the same example appeared in automorphism case. Our star has generators like this. It's because inner automorphisms PA and PB, PC, and PD are vanished in outer automorphism group. So there are no partial conjugations, and all the things that appeared in odd case, like connectedness of the commutative graph and rank 2 free abelian condition, also hold in outer automorphism group case. So we can deduce that out A gamma is not relatively hyperbolic. So that's it. That's the end of my talk. So let me stop here. Thank you.
Thank you. Let's thank the speaker. Are there any questions for the speaker? Okay, I guess I'll ask one.
Okay.
So I'm probably maybe I'm being silly, but
it's okay.
one point you mentioned the theorem saying that let gamma be a graph with at least 3 vertices, and then the right-angled Artin group is not relatively hyperbolic. What is the case if it has, say, 2 vertices?
Oh, sorry, I didn't understand your question.
Oh, sorry, I think it was theorem 1, or maybe it was. You said that let gamma be a graph with at least 3 vertices, then the automorphism group of the right-angled Artin group defined from that graph is not relatively hyperbolic.
You mean this outer automorphism case?
No, I think the theorem 1.
Theorem 1.
Theorem 1. So
what if it has, say, 2 vertices? Or is that just, or am I just?
Then it's either the free group or the Z2, I think.
Yeah, okay.
Sorry. No, if it has 2 vertices, they're either joined or they're not joined. So.
So is it clear?
Yeah, that's clear. Yeah, sorry.
Okay.
Just making sure.
Yeah.
Okay. Thank you.
Yeah.
The out result is really interesting, I think. Yeah.
Thank
I think
you.
that's really, really nice.
Thank you so much.
Yeah.
Or any other question?
Are there any other questions from the speaker? If not, let's thank the speaker again.
Thank you so much.
Thank you, and stop the recording.